We've already seen that magnetic fields exert magnetic forces on currents and moving charges according to these magnetic force laws. It turns out that currents and moving charges can also produce magnetic fields, and those magnetic fields then go on to exert magnetic forces on other currents and moving charges. So in this video we're going to look at the production of magnetic fields by moving charges and by currents. So first, the magnetic field due to a moving charge, we're going to assume that the charge is moving at much less than the speed of light. Otherwise, the expression becomes much more complicated and beyond the scope of this course. All right, so this is the magnetic field produced by a charge Q, a distance and direction r vector away from itself, so that r appears here with regard to magnitude and here with regard to direction in the expression. Mu naught is a constant, 4 pi times 10 to the minus 7 Tesla times meters divided by amperes. So this is a complicated expression and it has a cross product in it. So let's examine this cross product. And we need to be very careful. This cross product is between the direction the charge is traveling and the direction from the charge to the location where we want to know the magnetic field. So I'm going to mark the location that I want to know the magnetic field with this little question mark, and then later we'll consider this location and this location as well. But first, let's examine this location. So if I want to know the magnetic field produced at this location due to this moving charge, first I have to identify the charge's velocity vector. Then I draw an r vector line from the charge to the location where I want to know the magnetic field. Then in that direction, I draw my r hat unit vector. This is just a unit vector that points from the location of the charge to the location of where I want to know the magnetic field. Then I can go about taking this cross product. So remember, we got to use the right hand. So from magnitude, I could write a magnitude for this expression, and I'll write it down in just a moment. But to get the direction, I need the direction of this cross product, v cross r hat. So the direction of the magnetic field right here, well, first I've got to put my fingers in the direction of the V, curl them into the direction of r hat. My thumb points in the direction of the magnetic field at the location where I want to know it, right here. So V cross r hat gives me the magnetic field direction right here. Now I got to be careful. If the charge is positive, as it is in this case, then the magnetic field at this location will be in the direction of v cross r hat, out. If this charge were negative, the magnetic field would have been in, because that would have introduced a minus sign right here. So, for this case of a positive charge, the magnetic field right here is out of the board. I'll just say B is out. Now, let's do the same thing for this point right here. So I've got to draw a new r hat unit vector. Well, first I'll draw a new r. So there's a new r vector corresponding to this field location. I'll have a new r hat unit vector. R hat. And now I want to find the direction of the magnetic field at this location right here. I need to take the cross product of the velocity and the direction from the charge to the location where I want to know the magnetic field. So V cross r hat gives me the inward direction. So if this charge is positive, V cross r hat, that gives me the direction of the magnetic field right there. Magnetic field would be in. B is in at this location. Now, if the charge were negative, I would have my V cross r hat. I'd have the in for that, but then a negative charge would introduce a minus sign. The negative of in is out. So if this charge were negative, the magnetic field would be out. But it's positive, so it's in. All right, let's do one more. Let's consider this location right here. If I want to know the location, if I want to know the magnetic field right here, I need to draw myself an r vector from the charge to the location where I want to know the magnetic field. So here's my r vector. I need an r hat unit vector, which points in that direction. R hat. Now, again, we'll find the direction of the magnetic field right here. If the charge is positive, I've got positive stuff out here, and the direction of the field at this location will just be the direction of the cross product of V cross R hat. V cross R hat gives me a direction in. So, magnetic field is into the board at this location, assuming we have a positive charge. Again, if we had a negative charge, I'd have a negative sign in front of all those V cross R's, and all of these would be reversed. Okay. Now, let's look at those directions. Let's sort of summarize them. It turns out, and you can work this out for yourself, if we look at the plane of the board right here, I've got this charge moving to the right, and a positive charge, moving to the right. Anywhere above the charge, the magnetic field will be out of the board. Anywhere below the charge in the plane of the board, the magnetic field will be into the board. So we can sort of generalize that. Imagine I'm here looking and watching the charge, this positive charge, come toward me. Above the charge, as I look into the direction that the charge is coming from, the magnetic field above the charge is out of the board, and below the charge is into the board. So I can draw that right here. The direction of the velocity of the charge is out. I'll just write that here. Velocity is out. Now, so the charge is coming out like this. So we want to look at this again. As the charge is coming out, above here the magnetic field was out of the board. Let's just translate that right here. So locations above the charge, the magnetic field is this way. Similarly, as I look into the direction the charge is coming, for the charge is coming out at me, it's a positive charge, the magnetic field is into the board. I just translate that. So for locations right here, the magnetic field is this way. It turns out if you repeat this exercise, for a location right here, the magnetic field would be this way. For a location right here, the magnetic field would be this way. And so basically it's as if the magnetic field wraps around the direction the charge is going. So if the charge is coming out, you could curl your fingers around and they'd always give you the sense of the direction of the magnetic field. Positive charge coming out, stick your finger in the direction of the velocity of the positive charge, and your fingers give the sense of the direction of the magnetic field, wrapping around the direction of the velocity. Now, of course, if this were a negative charge, all of these would be reversed. All right, so I'm going to write down the magnitude of this expression, and then I'll consider the case of a current, which is very similar. To get the magnitude of this cross product, we take the absolute value of all the scalars out in front, and then we take the magnitude of this cross product here. I'd have magnitude of this, which would be V, magnitude of r hat, which would be 1, because the magnitude of any unit vector is 1, and then the sine of the angle between these vectors. And this is the magnitude of the magnetic field produced by a moving charge, moving at much slower than the speed of light.